In this video, we're going to consider the simple and instructive example of a loop of wire, a square loop, being pulled out of a uniform magnetic field, and we figure out what is the induced current and also what is the direction of the induced current. So here's the square loop that we are interested in, and it's situated in a magnetic field which is going into the board as shown by the X marks, and the magnetic field only exists within this square region. And the loop is being pulled out at a constant speed v towards the right. The induced EMF in the loop, because while it was totally inside the magnetic field, there was a certain amount of flux, and as the right side edge of the loop moved away from the region of the magnetic field, the flux threading through the loop starts to decrease, and that induces a current which is due to an EMF, and that is given by Faraday's law, of course. And what is the sense in which the current should be induced, and what is the magnitude? To figure the magnitude, we can write the following equation. The change of flux at any given time t is simply the magnetic field, since it's constant, times the change in the area. The change in the area is how much of the length of the loop is being pulled out in that time t, which is this, times the vertical distance d. This we can write as delta phi b delta t equals to b v d, because we have divided this out on both sides by the time that it takes, and therefore the EMF is simply the magnetic field b times the velocity times the height d. The direction, of course, is given by Lenz's law. Since the loop is getting out of the magnetic field, the flux in the loop is decreasing, and this means that the current has to be in such a direction as to produce the same flux that it had before. And that direction, by using the right-hand rule, tells us that it should be into the bore, and therefore the current has to be in the clockwise direction. There is another way of looking at what is happening physically here. This is in terms of the force felt by the moving charges in this loop. So let's consider the charge while it is moving in this part of the loop on the left-hand side, and it's moving with a velocity v. And therefore, in terms of the Lorentz force, this moving charge experiences a force qv cross b. And since we've learned about the cross product and how to figure that out, the resultant of the cross product is such that the force will be upward. So we have the velocity v like this, and the magnetic field going into the board. And if we think about a right-handed screw, the way that the wrench would turn in order to go from the direction of v to the direction of b, the screw would move upwards. So the force is in the upward direction. Since the charge has experienced a force, there has to be an electric field, and this electric field is also upwards, and its magnitude is going to tell us what is the potential difference between these 2 points. Electric field is simply the potential difference divided by the distance d, and since we figured out what is the electric field, which is the force per unit charge, which is v times b, since v and b are perpendicular, we don't have the sine theta. This cross product is simply v times b times q. But since we're interested in the force per unit charge for the electric field, that's simply v times b. And of course, the electric field times the distance here will give you the potential difference, which is V times B times D. And this is indeed the induced EMF that we found before. Now, what about the moving charges in the horizontal segments, as shown here? They will also experience a force and there will be an electric field, but in our example here, the thickness of the wire is negligible. So even though there may be a potential difference in this direction, we ignore that.